Hello everyone, welcome to Jet to Mastery. In this video, we are going to learn asymptotic analysis of algorithm or BIGO notation. BIGO. So this is the video we are going to learn what is the steps to calculate BIGO notation, and we are going to deeply discuss about BIGO. Okay. So first of all, what is the use of BIGO? So the uses of BIGO is we can compare the two algorithms over a large inputs. So that is the main purpose. Okay. So let's discuss what are all the steps to calculating BIGO notation we need. The first step is calculate number of iteration. So we have learned how to find the number of iteration based on the given input, right? Okay. The first step is calculate number of iteration. The second step is reject. Okay, neglect or reject. Reject lower order terms if it is in addition or subtraction. The third point is reject constants. Constant is nothing but the number. Okay, number. Okay, so this is the comparison order. Okay, so comparison order. The first comparison order is log of log n. This is less than log n. Yes, absolutely. This log n is a less than root n. This root n is a less than n. So n is a less than n log n. So n is, I am talking about the given input. At the end of the time, we are finding the number of iteration. No? I am talking about that. N is a given input. Then these are the number of iterations. So n log n is a less than n root n. N root n is less than n square. N square is less than n cube. N cube is less than 2n. 2n is less than n factorial. N factorial is nn. And I would like to say one thing. This BIGO will work only when we have a larger input. Okay, so the main purpose of BIGO notation is to compare the two algorithms when we have a larger inputs. This is not I'm not talking about when we have a very smaller inputs, right? Because very smaller inputs, we no need to calculate anything because it will work fine whatever our iteration. Okay, so this is for only when we have a larger input, we are calculating the time complexity. For that purpose, it will be helpful. So let's understand. So as of now, these two things are my number of iteration. Let's consider this is one number of iteration for the separate program, and this is one number of iteration for the separate program. So just follow the rule one by one. The first thing is calculate the number of iteration. Okay, I have calculated two things. Okay, I have a two number of iterations there. Now how to calculate BIGO? Okay, that is the question. See, 4n plus n log n. 4 is a constant, so we can directly, this is the third rule, right? If it is a constant, we can ignore. So I have ignored 4 as well as this one. Okay, fine. Then n plus n log n. Which one is a lower order term? N is a lower order or n log n is a lower order? N is a lower order. See, n less than n log n. So I can ignore this n as well. So what is the remaining thing? N log n. Here you can say n is there and log n is there, so we can ignore this log n, we can say n. No, we can ignore the lower order terms if it is in addition or subtraction. These n log n is in the multiplication part, so I can't ignore. Okay, so in this case, my order of n is, my BIGO notation of n is, the answer is order of n log n. So this is my answer. Okay, let's take 4n. Okay, in this case 4n, 4 is a constant, ignore. 3 is a constant, ignore. 10 power 5 is a constant, ignore. Fine. Then what is the lower order term? N log n is there, n root n is there. Which one is n log n? Okay, n log n is less than n root n. So this is the lower order term, so I can ignore. So what is my answer? My answer will be n root n. Order of the BIGO of n root n. So this is my answer. I can say this is my answer. Now you may raise your question, right? You can ask one question. Why we need to ignore the lower order terms? Calculate the number of iteration. Okay, I can get it. Why I need to redact the lower order terms and these constants? Okay, so I will tell you the one example, then you can understand these two steps. Why we can ignore constants and lower order terms. Okay, so let's understand here. Why? We can neglect lower order terms. Let's consider my number of iteration is n square 10n. Okay, n square 10n. So what is the lower order term here? 10n is the lower order, right? 10n is the lower order because this 10n is less than n square. As of now, reject 10, then n is less than n square, so I can ignore the 10n. So I can say n square is my order of n square is my time complexity, like that. Okay, so let's take my n is 10, my n is 10. Okay, what is the total iteration? 10 square plus 10 into 10, that is 200. In the total iteration, how much percentage of lower order term contribution? I am just calculating the lower order term contribution. Okay, 100, this 10n is the lower order term, right? Lower order term. So fine. So in the 100 is 50% is contributing, even if your n is 10. Let's take your n is 100. Okay, so if n is 100, total iteration n square, so 10 power 4 plus 10n, so 10 power 3. Okay, so this is my total iteration. In the total iteration, how much percentage my lower order term will be contributing? So that is, I have calculated previously I have calculated just for saving our time. So the percentage is 9%, from 50 to 9%. Yes, the very huge difference, just because I am adding 1 zeros extra, right? Okay, let's take my n is 10 power 4. Okay, if my n is 10 power 4, it's a larger input. Okay, these 10 and 100 are very lower order term. See, very lower inputs, and this big O notation is only for larger inputs, right? So let's take, this is my larger input. So if I have a larger input, what is the total iteration? 10 power 8 plus 10 power 5. In the total iteration, how much percentage my lower order term will be contributing? That is 0.1%. It never affect your number of iteration. It never affect your performance of the algorithm. So that we are rejecting lower order terms and constants, everything, right? See, why we can neglect means, when we have a larger inputs, the percentage of lower order term is very small, very small. It won't affect our performance of the algorithm. So that we can ignore, so that we can reject lower order terms as well as constants. I hope you have understood this asymptotic analysis of algorithm or big O notation. So in the next video, we will calculate more and more big O notation. Then we will calculate the time. Big O notation is nothing but we have calculated here, right? The same thing. This is the order of n log n. Here we can say this is my time complexity. It's very simple. So in the next video, we will solve more and more time complexity and space complexity. How to find time complexity and space complexity. I will catch up in the next video, guys. Until then, stay tuned with me. Bye bye.